Good morning, everyone. My name is Rutt. I'm a graduate student in the Pearson group, and I'll be leading today's lesson on automated DFT. So if you are following along in CoCalc, I'll go through where we navigate to that in a moment. So if we start off in our project, and then in the home directory, we're going to go to workshop, lessons, and then 05 automated DFT. And so I'm going to be working in a blank notebook, but all the content we'll be going through is contained in this lessons notebook. And we'll be getting started in a few minutes. Okay, good morning again. Let's get started. Once again, my name is Rutt. I'm a graduate student in the Pearson group, and I'll be leading today's lesson on automated density functional theory. So this lesson focuses on key concepts necessary to run automated density functional theory, or DFT, workflows using our Automate code. We'll be following along the documentation on the MP Workshop website under Workshop, Day 2, Automated DFT. There are 3 core concepts for this lesson. First, in lesson 1, we'll go over how to use the I/O or input-output module of PyMagen to write input files. In lesson 2, we'll go over code in PyMetGen and Animate for parsing output files. And lastly, in lesson 3, we will demonstrate how everything is combined for database automation for running DFT calculations. So let's go over to CoCalc. And we'll be working again in this workshop lessons 05 automated DFT directory. And we are going to be using some example files from this directory, so it's important that you are working from a notebook that has access to these files. So for today's session, I'll be typing into blank Jupyter notebook on CoCalc, but you're also welcome to refer to the content on the website or in the lessons notebook in CoCalc under this directory. So this lessons notebook has the same content that's also on the website. Okay, so let's start our new notebook. And I'm going to name this lesson 1 to keep things organized. And then I'll add a few new cells. Okay, so once again, I want to note that we'll be using a few files that are provided in this 05 automated DFT directory. So several of them are in this folder example files. So you can open it up and see there's a few different files that we'll be working with for the lesson and the exercises. And then there's also a couple of example directories that we'll use of output calculation files. Okay. So if we go back to our blank notebook, the first thing that we need to do to get started is to run import MP workshop so that we have the variables we'll need for our lesson. So I'm going to type import MP workshop and shift enter to run that cell. Okay, so PyMetGen is really helpful for simplifying how we interface with external DFT codes. These external codes are written in coding languages other than Python, like Fortran, C, or C++. But PyMetGen's I/O module allows us to interface with them all through Python. For today's lesson, we'll focus on one of these codes, VASP, which is a DFT code for atomic scale materials modeling. VASP is the DFT code used by the materials project for inorganic crystals. We'll also use a second DFT code, Qchem, in the exercises, which is used by the materials project for molecules. So let's begin by obtaining a silicon structure to use in our first lesson. This structure will come from a CIF file in our example files directory. So we're going to be importing this si.cif file. Okay, so the first thing that we need to do is import our structure object from PyMetGen. So from PyMetGen.core import structure. And then I'm going to call this variable struct for structure. So struct is equal to structure from underscore file. And then file name is equal to, so period slash for the current working directory. And then example files to go into that directory. And we're pulling out this si CIF file. Okay, and then let's print out our structure to see what we've imported. So print struct. So we should see a silicon structure with about 8 atoms in it. VASP has 4 types of input files that must be provided by a user to run a calculation. There's the incar, which specifies modeling parameters for how to run the calculation, a poscar file, which provides the atomic structure, and this is the one that we'll be focusing on shortly. There's also a kpoints file that outlines points for sampling space in the simulation cell. And lastly, a podcar file that describes how to simulate the electrons with pseudopotentials. So PyMetGen has Python objects for representing each of these 4 input files. So since we'll be focusing on the poscar, let's import a poscar object from PyMetGen. So from PyMetGen.io.vasp.inputs, import poscar. Okay, and now we can obtain a poscar Python object using the silicon structure from before. So let's call this poscar. So poscar is equal to poscar. and then parentheses. And if we press Shift Tab, we can look at the docstring and see that to initialize this pause car object, we need to provide a structure. So let's say structure is equal to struct for our silicon structure from before. And I'm also going to take advantage of this comment argument to add a comment to label our structure as silicon. So comment is equal to silicon. And then let's print out our pause car to see what it looks like. So print pause car. So we can see that we have our comment for silicon, and then we have this 8-atom silicon structure contained in it. So since we can access the pause car structure through Python, we can make modifications to the structure all using PyMetGen before turning the structure into a pause car file. So for example, let's introduce a defect by removing the first site from our 8-atom silicon structure. So if we do pause car dot structure, this is how we access the structure contained inside. And then I'm going to use the method remove sites. So remove underscore sites. And if we press Shift Tab, we can see that we need to provide a list of indices for the sites that we want to remove. So I'm going to do square brackets to start a list, and then just remove the first site with 0. And now we can print out our pause car once more to see how it's changed. So print pause car. Okay, so now if we look at it, we see that we only have 7 silicon atoms, and the first atom, which was at 025, 025, 025, has been removed. So now let's write out a pause car file from our pause car object using a method for writing out the file. So this method is called write file. So we're going to access pause car dot write underscore file. And then parentheses and Shift Tab. So in the doc string, we can see that we need to specify a file name for where we want the file to go. So I'm just going to call this file pause car. So file name is equal to pause car in all caps. Okay, so if we go back to our automated DFT directory, we should see that we now have this new file created called pause car. So again, it looks pretty similar to what we printed out, where we have 7 atoms for a silicon structure. Okay, if we go back to the lesson. Another common situation is wanting to obtain a pause car object from a pause car file that already exists. The pause car object also has a method for reading in a pause car file. So if we go to our example files, let's try reading in this pause car file that's zipped over here. So I'm going to call this variable pause car from file. So pause car from file is equal to our pause car object, and then the method from underscore file. And if we press Shift Tab, we can see that for this method, we need to just specify the file name for the file we want to read in. So file name is equal to a string and then period slash for the current directory. And then we're going into example files and pulling out the pausecar.gz file. And then we can try printing out this pause car from file. So print pause car from file. Okay, so if you have an aluminum chromium structure, you have correctly imported this pause car from the example files. So the other VASP input files like the incar, kpoints, and podcar all have similar method to the pause car for initiating objects and writing out files. It can still take quite some effort to explicitly generate all 4 input files needed for a VASP calculation. So to further automation, PyMetGen builds upon these pieces to generate what are called input sets. So if we continue with our silicon structure from before, we can generate the remaining VASP input files we need for a calculation using input sets. And specifically, let's generate the input files for a structure relaxation with parameters similar to the materials project using the input set called mprelaxset. So the first thing that we need to do is import our mprelaxset object. So from pymetgen.io.vasp.sets import MP relax set. Oh, and I have a typo, so let's fix that and spell VASP correctly with a P. Okay, so to initialize our input set object, I'm gonna call this relax set. So relax set is equal to MP relax set, and then parentheses shift tab. So we can see the only thing we need to provide to initialize our MP relax set object is a structure. So we'll do structure is equal to struct to grab our 8-atom silicon structure from the beginning, and then run that cell. And now within this relax set object, we can access the Pythonic object for each of the VASP input files. So first we can look at relax set incar, so relax underscore set dot incar. So we can see this gives us a dictionary of the incar parameters that would be used for this calculation. Next, we can check the poscar, so relax underscore set dot poscar. So this should look familiar where we're printing out our poscar object for silicon. And then we can also look at the K points. So relax underscore set dot K points. So this is going to outline our K point density for the calculation. And then lastly, we can look at relax set dot potcar. So if we just print out the potcar attribute by itself, we don't get that much information. So I'm going to add the method .as underscore dict, and that will give us a little bit more. So we can see that we have a PBE functional for silicon. So now in order to write out these 4 VASP input files, there's a method called write input that we can use. So relax underscore set dot write underscore input, and then parentheses shift tab. So here we can see that we just need to provide an output directory that's going to specify where we put our input files. So I'm going to do output underscore dir is equal to a string and then period slash for the current directory. And you can call this directory whatever you'd like to. So I'm going to call this SI MP relax set since we're using a silicon structure and MP relax set parameters. So SI underscore NP relax set. And then press shift enter to run the set wall. So now we can check cocalc for that directory to see the files that have been written. So if I go over to files, we see that we have this new SI underscore MP relax set directory. And as we would hope, it has our 4 VASP input files. So it's the incar, K points, poscar, and potcar files. Okay, so that's the end of lesson 1 for writing input files. So now we can shift over to the exercises notebook for some practice with writing input files. So if we go to our 05 automated DFT directory, and then open up this exercises notebook here. So I'm going to open that up and select a kernel. Okay, so the first thing that we need to do for this notebook is to run this MP or import MP workshop cell. And you want to make sure you do this as your very first thing. And there is a typo, so make sure that you fix that to make this import MP workshop. Okay, and if it's run correctly, you should see this echo test. And then we are providing with everyone with these 2 structures to use in the exercise. So there is an aluminum chromium structure that's stored in this variable struct, and then an ethylene carbonate molecule that's stored in this variable mole. So you'll also want to run these 2 cells before starting your attempt on the exercises. Okay, in exercise 1.1, our goal is to write out the VASP input files for the aluminum chromium structure Instruct. And rather than using MP relax set as we did during the lesson, we're going to use a different type of input set object called MP static set. So we have a few cells for you to work on that there. And then we have a second exercise, exercise 1.2. In exercise 1.2, our goal is to write out Qchem input files for the ethylene carbonate molecule in mole using the opt-set input set object for Qchem, which is for a molecule optimization. So we're going to go through the similar steps of needing to import our input set object, initializing the input set object, and then figuring out the method to write the object. But now instead of VAST, we're going to be using the code built in for Qchem. So let's give everyone about 5 minutes to work on these exercises, and we'll come together to go over the solutions at around 9:40. Okay, so let's come back together to go over the solutions for exercise 1. So make sure again that you have run these 3 cells and have done import MP workshop first. So for exercise for 1.1, the first thing that we need to do is import our input set object, MP static set. So this line is similar to what we have for MP relax set. So from pymetgen.io.vast.sets import MP static set. And then shift enter to run that cell. And then the next thing we need to do is initialize our input set object. So I'm going to call this static set. So static underscore set is equal to MP static set. And then if we do parentheses shift tab, we can see that it's pretty similar to MP relax set, where the only thing we need to initialize it is a structure. So let's say structure is equal to struct. So this is going to grab our aluminum chromium structure that was provided earlier. And then the last thing we have to do is use the method to write out the input files. So static underscore set dot write underscore input. And then parentheses shift tab. So we just need to provide a string for the output DRI. So output underscore direct is equal to a string and then period slash to refer to the current directory. And we can call this again whatever we want. I'm going to call it ALCR MP static set. So ALCR underscore MP static set. And then we can try running that cell. So we see that we get this little warning that's part of the value of pymetgen, where it can tell us sometimes if we're using VAST parameters that are not appropriate for the structure provided. But either way, let's go over and look at the files to see if we correctly wrote out our files. So we can see that we have this new ALCR MP static set directory. And if we go inside of it, it looks like everything checks out, where we have our 4 VAST input files, the incar, kpoints, poscar, and podcar. Okay, so that's the solutions for exercise 1.1. So let's go back to our exercises notebook and look at exercise 1.2. Okay, so same steps, but now we have to adapt them for Qchem. So the first thing that we need to do is import the offset input set object from Qchem, or for Qchem. So from pymetgen.io. So here, now rather than using the VAST module, let's use the Qchem module instead. So Qchem.sets, and then we can import offset, and then shift enter to run that cell. So it looks like that imported correctly. So we found the correct import statement. And then we need to initialize our input set object. So opt underscore set is equal to opt set, and then parentheses shift tab to look at the doc string. So here we need to provide a molecule object instead of a structure object like we did before with our VAST inputs. So let's say molecule is equal to mole for our ethylene carbonate structure. So molecule is equal to mole. Okay, and now let's see if we can find the method for writing out the input files. So opt underscore set, and I'm going to do period tab. So we can see that there are a bunch of different methods, and they might not be the exact same as the ones that we had for our VAST input sets. So I'm going to start writing out write to see if that helps us figure out the name of the method we want to use. So I'm just going to try this first one, write. So write, and then parentheses shift tab. So here we can see that we just need to provide an input file, and that will name the file that's written. So input underscore file is equal to, and again, we can call this whatever we want. I'm going to call this EC input. So EC as a shortcut for ethylene carbonate input. and then Shift Enter to run that cell. So we can go back over to our files, and it looks like we do have this new file EC input. So this contains the parameters that would be needed to run a Qchem calculation. And that's the end of the solution for exercise 1.2. Okay. So now let's start a new notebook to move on to lesson 2. So I'm going to close some of these tabs and then create a new notebook, which I'm going to name lesson 2 to try to keep things organized. Okay, and we'll add a few new cells here. Okay, so take a deep breath to pause before we dive into the exciting world of parsing output files. Okay, so now let's start on lesson 2, which focuses on parsing output files. For this portion of the lesson, we'll focus on the example output files in one of these directories. So now we're going to be looking at this example VASP AL16CR10 directory. Okay, so if we go back to, well, I guess one other thing that I'll mention before we go back to the notebook is that in this directory, for the first part of the lesson, we're going to be focusing on this vastrun.xml file here. Okay, so let's go back to our blank notebook. And the first thing we need to do if you started a new notebook like me is import mp_workshop. Okay, so as I said, first we're going to look at the data that's stored in that vastrun.xml.gz file. Similar to how PyMetGen has objects corresponding to input files, PyMetGen also has objects corresponding to output files, like the vastrun Python object that we'll be using. So let's start by importing this vastrun object. So from pymetgen.io.vasp.outputs, import vastrun. Okay, and as a shortcut for vastrun, I'm going to call this variable vrun. So vrun is equal to vastrun, and then parentheses shift tab. So here we can see that in order to initialize our vastrun object, we need to specify the file name for the vastrun file that we want to import. So I'm going to do file name is equal to a string and then // for the current directory. So we're going into this example VASP AL16CR10 directory. So example _ VASP _ AL16CR10. And then we're grabbing the vastrun file. So vastrun.xml.gz. And then let's run that cell. Okay, so now that we have this vrun object, we can use vrun + tab to check out the properties for the vastrun object and see what data we have from our VASP calculation. So for example, I can do vrun dot. You can see all the different methods and attributes that are stored with this. I'm going to start off with one that's pretty important called converged to tell us whether or not the calculation has converged. So converged and print that out. Okay, so it's true that indeed our calculation is converged. So that's good news for us. And then another useful method is vrun dot final structure. So this is going to give us our structure object that's produced at the end of the VASP relaxation. So vrun dot final structure. So you can see this gives us a PyMetGen structure object for aluminum chromium, and this is how it's changed at the end of the calculation. And then one other thing that I'll mention, you might have noticed it when we were searching for the final structure attribute is vrun dot final _ energy. So this is giving us the energy produced by our VASP calculation. Another useful set of data is stored under the attribute ionic steps, where information on how the calculation progressed is stored. So if we check the length of V-run ionic steps, we can see how many ionic steps were taken during the course of the calculation. So let's use the length method. So length and the parentheses, V-run dot ionic steps. So if we print this out, this will tell us how many ionic steps were in the calculation. So we have 4 in this situation. And if we look at the keys for one of those steps, we can see what properties are stored. So if we do vrun.ionic underscore steps, and this is a list, so we can look at the first attribute, and it is a list of dictionaries. So we can look at the keys of the dictionary to see what kind of data is stored. So let's add a dot keys. Okay, so for every single ionic step, these are the different properties that we have stored. So let's try looping through each ionic step to see the energy and how many electronic steps were required. So for the energy, we're going to use this E_FR_energy property. And then to look at how many electronic steps there are, we're going to print out the length of the electronic steps field. So to do a for loop, we're going to start with for and then I in vrun.ionic steps. So I is going to be representing each individual ionic step as we loop through. And then a colon. And we're going to print out our 2 different properties we're interested in, the energy and the number of electronic steps. So print, and then we're going to do I square brackets E_FR_energy. And then for our second attribute, we're going to use the length function again. So length of I square brackets electronic steps. So let's run that. So we see that for our 4 ionic steps, this is how the energy has changed. And then this is the number of electronic steps that we have. Okay, so to further automate parsing output directories, let's introduce the concept of drones from the Python code Automate. Automate drones can parse entire calculation directories using a method called assimilate. And the output of this assimilate method is a dictionary summarizing the calculation results. And this dictionary representation is helpful because it can be stored in a database like we do with the materials project. So let's import our drone object from Automate. I'll add a few new cells here. Okay, so let's import our drone object from Automate. From automate.vast.drones, import vast drone, and then run that cell. So we need to initialize our drone object. So I'm just going to call this drone in lowercase. So drone is equal to vasp drone, and then parentheses to initialize the class. So now to use the drone, let's store the results in a variable called task_doc. And we can assimilate the example vast AL16 CR10 output directory where our vast run XML file from before came from. So if we go to files, we're going to be assimilating this entire directory here that contains several of these different types of output files from vast. So as I said, we're going to call this variable task_doc. So this is going to be a dictionary of our results. So task_doc is equal to, and then we're going to use this assimilate method from the drone. So drone.assimilate. And parentheses. And if we press Shift Tab, we can see that the only input we need to provide is the path for the directory that we want to assimilate with this drone. So let's say path is equal to, and then start a string, / for the current directory. And then we're going to do the example vast AL16 CR10 directory. So example vasp_AL16 CR10. And then run that cell. It might take a little bit of time. So you can see that it's finished running. And now let's see what information is in this task doc variable we've created. So it's a dictionary, so I'm going to print out its keys. So print task underscore doc dot keys. Okay, so it seems like things parse correctly, and we have a bunch of different properties here, like the chemical system, the composition, some input and output data. So we're going to use the exercises to explore the information contained in the task doc a little bit more. And this is the end of lesson 2 on parsing output files. So we have 2 exercises in the exercise notebook for experimenting more with parsing outputs. So let's go over to our exercises notebook. Okay, so we have 2 exercises in exercise 2. So there is a slight typo. This should be exercise 2.1. Okay, so in exercise 2.1, we have some questions for exploring the task doc that we just produced with a drone from the directory example VAS AL16 CR10. So in order to have the task doc that we produced in the lesson, you're going to want to run these 3 cells before you get started. And this will just let you pick up essentially where we stopped at the end of lesson 2. And we have 3 questions. So trying to figure out how many sites are in the calculation structure, which is stored in the task doc, finding where the final energy is stored, and then also what the final energy per atom is. And then comparing our answers to make sure that everything makes sense. And then we have exercise 2.2. So this one is rather tricky. Here we're asking you to figure out how to use an Atomate drone to parse the outputs in our directory of Qchem example files. So we're going to be parsing the outputs in this example Qchem ethylene carbonate file. And if we go inside, we can see that we have a different type of output files since these are coming from Qchem. So we have this mol.qin, which is an input file, mol.qout, which is an output file, and then solvent data. So let's give everyone about 5 minutes to work on these exercises. So we'll come together again at about 10:02 a.m. Okay, so let's go over the solutions for exercise 2. So first we'll do exercise 2.1. And the first question we have is how many sites are in our calculation structure? So as we did before, let's print out the task.keys to see where we might want to navigate to. So I'm going to do task_doc.keys. Okay, so if we see we have this n sites attribute, that seems pretty promising for finding out the number of atoms in our structure. So we can do task_doc and then square brackets n sites. And I'm missing an S, so let's try that again. Okay, so we have 26 atoms in our structure. Now the second question is finding the final energy. So if we go into this output field, that's probably a good place to see where our output data is. So task_doc, and I'm going to explore the keys for this output field to see where we want to go next. Okay, and one of these fields is called energy and energy per atom. So this energy one is probably the output energy we're going for. So task_doc, square brackets, output, square brackets, and then let's print out the energy. Okay, so the energy here is -157.8, and that does match the number that we got from our lesson 2 analysis. And for question 3, we're looking at the energy per atom. So let's print out task_doc. And now instead of just energy, we're going to do output energy per atom. Okay, and then just a final check to make sure everything makes sense. Let's divide the output energy by the number of sites to make sure that matches. So I'm going to copy this value over and divide by 26, our number of atoms. And we can see that our two numbers do match. So everything looks good and is making sense. So that's the end of our solutions for exercise 2.1. Now, if we shift over to exercise 2.2, where we're looking at parsing Qchem outputs, the first thing that we need to do is import a drone appropriate for Qchem. So I'm going to add a few cells, so I'm not typing at the bottom here. Okay, so from Atomate, and now we're going to use the Qchem module instead of VAS. So Qchem.drones import Qchem drone. So that's the name of the drone for Qchem. And now we need to initialize our drone object. So I'm going to call this QC drone. So QC_drone is equal to Qchem drone. And then parentheses and run that cell. And now we need to assimilate the example Qchem ethylene carbonate directory. So I'm going to call our dictionary of outputs QC taskdoc. So QC_taskdoc. And then this is going to be equal to Qchem drone. We're going to use the assimilate method. So assimilate. And now if we do parentheses shift tab and look at the doc string, so here we can see that we need to specify a few more things to assimilate a Qchem output directory. So like before, we have the path. So path is equal to / for the current directory. And then it's called example_Qchem_ethylene_carbonate. And then the next output we need to specify is input file and output file. So again, if we go into the files and look at our directory, this mol.qin is the input file and mol.qout is the output file. So let's type that in. So input_file is equal to mol.qin.gz. And output file is equal to mol.qout.gz. And then the last variable we need to specify is multi-run. So this is telling the drone whether or not there's multiple calculations in the same directory. And since we only have one input and one output file, that's going to be false because we only have one run. So our last one is multi-run is equal to false. And then let's try to run that cell. Let's see, so I think we did initialize our Qchem drone correctly.
I think you want QC_drone.assimilate, not Qchem drone.
Can you say that one more time, Sean?
I think you want the QC_drone.assimilate,
yes,
not
you're
Qchem
right.
drone class.
Thank you. So we're not using the class itself, but the object we initialized. So hopefully you didn't make that mistake if you were going through this yourself. Now let's try that one more time. Okay, so it looks like we don't have an error. And then to double check that it did parse some data, let's print out the keys for QC task doc. So QC_task doc dot keys. Okay, so if you have some different fields for this dictionary, it looks like things were parsed correctly. And that's the end of our solutions for exercise 2. So we can take a deep breath before diving into lesson 3, which is our last segment. And there will be no exercises at the end of lesson 3. So it'll just be a demonstration that we can follow along with. Okay, so I'm going to close these notebooks. And once again, I'm going to start a new notebook for lesson 3. So let's label this lesson 3. Add some new cells. Okay, so Atomate provides a set of recipes for computing properties for both molecules and structures. The workflows in Atomate run on Fireworks, which is our workflow management software. Fireworks stores workflow information and calculation summaries in MongoDB databases. And this is the infrastructure that we use for the materials project. So the first thing that we need to do is import MP workshop. Once again, if you're starting a new notebook, so MP_workshop. Okay, so the first part of the demonstration will be getting workflows from Atomate. So let's begin by importing the same silicon structure that we used in lesson 1. So from PyMetGen.core import structure to get our structure object. And then instead of struct, let's call this SI to be a little bit shorter. So SI is equal to structure from file. And then parentheses, we need to specify the file path. So // for the current directory, and then example_files/si.cif. And then we can print out SI to make sure that we have the correct structure imported. So we have 8 silicon atoms, that looks good. So far in the lesson, or in this session, we've gone over some of the machinery used to automate DFT calculations. Atomate workflows with the support of Fireworks compiles everything needed to store workflow inputs from the user, create new calculation directories and write input files, and parse output directories and store the results in a MongoDB database. We can import workflows from Atomate, which are essentially the recipes that outline the steps for how to automate calculations from start to finish. For this demonstration, we will focus on 2 types of workflows for VASP: the structure optimization workflow, which is simpler, and advanced structure workflow, which is more complex. So let's get started by importing these workflows and then creating workflow objects from our silicon structure. So let me add a few more cells here. So to import our workflows, we'll use from atomate.vasp.workflows.presets core. And we're going to import WF underscore structure optimization, which is our structure optimization workflow, and WF underscore band structure, which is going to give us our band structure workflow. Try running that cell. And then we need to get our structure optimization workflow object. So I'm going to call this SOWF for short. So this is going to be equal to WF structure optimization. And if we do Shift Tab to look at the doc string, we see that we just need a structure object to initialize this workflow. So structure is equal to SI. And then we can print out this SOWF object to see what it looks like. Okay, and now let's get our band structure workflow. So I'm going to call this BSWF for short. And now we're going to do WF underscore band structure. And similar to the structure optimization workflow, the only thing we need to provide is a structure. So structure is going to be equal to SI once more. And now we can print out the BS workflow object. So print underscore BS workflow. So you can see that for a more complex band structure workflow, we have more fireworks in it than the simpler structure optimization workflow. And let's see a graphical representation of each of these workflows, so this will be clear. We can import a method called workflow to graph to help us. So let's import this method from np underscore workshop.animate import WF to graph. And then we'll use it on our two workflow objects, so WF to graph, SOWF, and then WF to underscore graph, BSWF. So we can see that the structure optimization workflow is simpler because it only contains one firework. The band structure workflow has 4 fireworks, so we can assume it's more complex. The exact steps in each firework can vary, but for these cases, each firework or each square roughly represents one VASP calculation, which consists of the following steps: writing the VASP input files, second, running VASP, and then lastly, parsing VASP output files. In the band structure workflow, we can see the fireworks are connected. That means the outputs from one firework are passed to the next firework so that VASP calculations can start from the relaxed structure of the previous calculation. For our demonstration, we'll need to make a modification called use fake VASP workshop to our workflows. This will change the fireworks in the workflows so that they will not actually run VASP, which requires greater computer resources and a VASP license, but instead will simulate running VASP by copying over pre-existing VASP output files. So let's import this method. From np underscore workshop dot animate import use fake VASP workshop. And then let's apply it to our 2 workflow objects. So SOWF is equal to use fake VASP workshop, SOWF, and then apply it to the band structure workflow. So BSWF is equal to use fake VASP underscore workshop, BSWF. Okay, now that we have our ready workflow objects, let's go over how to run them. To run our workflows, we will introduce the Launchpad from Fireworks, which is a Python object that lets us interface with MongoDB and manage our queue of calculations. The Launchpad allows you to submit and query workflows from anywhere you have database access. So let's set up a Launchpad object that will let us run our workflows. So from Fireworks, import Launchpad. And then I'm going to call this Launchpad LP for short. So LP is equal to launchpad.auto underscore load. Okay, so that initializes the Launchpad object. And then we're going to reset our Launchpad. Note this should only be done one time when you're first initializing your setup. Otherwise, you'll erase the records from your past calculations. So we need to do lp.reset. So we see that we need to provide a password, and we're going to change this required password flag as well. So let's just say password is equal to none, and then require password is equal to false. Okay, so now let's add our structure optimization workflow to our Launchpad. This will encode and store a workflow object in MongoDB so it can be accessed when we need it. Okay, so let's add the workflow. So lp dot, and we have a method called addWF. So add WF. And then we can give it our structure optimization workflow, so SOWF. And we have indeed added our workflow to the Launchpad. And now that the workflow is in the Launchpad, we can check on its status using the method getWFSummaryDict. So let's use it. lp.getWF summary underscore dict. And we need to specify firework ID equals 1 so it knows which workflow to grab. So let's run that. And we can see that we have a ready workflow. So the state says ready. And that means that we're ready to run it. So normally we run our workflows through Fireworks on a supercomputer, but for today's demonstration, we'll run our workflows locally in this notebook so we can see what's happening. Fireworks has a command called rlaunch for running a firework that is in a workflow from our Launchpad. So let's use the command line to look at this command. So exclamation mark to go into the command line, and then rlaunch. And then let's do -- help to get a little bit more information about this command. So we can see that the rlaunch command requires one of 3 arguments, single shot, rapid fire, or multi. So we're going to use rapid fire mode, which will mean that it will launch rockets continuously until all fireworks have been completed. So let's go ahead and do that. So exclamation mark to run this in the command line, and then rlaunch rapid fire, and then shift enter to run that cell. So we'll give it a few seconds to run and simulate doing a VAS calculation by copying over the files. And now that our workflow has been run, let's use the getWFSummaryDict method to see how it's changed. So lp.get underscore workflow underscore summary underscore dict. And we need to specify firework ID equals 1. Okay, great. So you can see that the state of our workflow has changed from ready to completed. And if we go over into our files, we'll see that we actually have this newly created directory called launcher where the calculation was run. So let's go back to our lesson. Now let's try running the more complicated band structure workflow, which has 4 fireworks in it. So let's first add the workflow to our Launchpad and look at its summary dict. So lp.add underscore WF, and then BS underscore WF. And then let's look at the summary dict. So lp.get underscore WF underscore summary underscore dict. And now we're going to specify firework ID equals 2 to get the band structure workflow. So once again, we can see that the state of the workflow is ready. And we have 1 ready firework and 3 waiting fireworks. So now let's use the rlaunch rapid fire command again to run this workflow. So exclamation mark, rlaunch, rapid fire. So this will need several seconds to run since we're going through 4 fireworks instead of just 1. Okay, it looks like that's finished now. So we can check out the workflow again with get WF summary dict to see if it's completed successfully. So lp.get _ WF _ summary _ dict. And then we need to specify firework ID = 2 to get our band structure workflow. So now we can see the state of the workflow has completed and our 4 fireworks are completed. And if we go into our files, we can see that we now have 4 new launcher directories as well. So each of these is corresponding to one vast calculation and kind of has all the files for the inputs and the outputs since we've completed the workflow. So the last thing I'll mention is that Fireworks also has a command called qlaunch to automatically submit jobs to supercomputers to run. So as a Fireworks user, it's actually more common for you to use this qlaunch command instead of rlaunch because rlaunch will be called automatically when the job starts in the supercomputer. So that's the end of our demonstration for Lesson 3, Database Automation. Thank you for joining us on the session about automating DFT.